Welcome to homework.
Hello. Today we'll be talking about Chapter 15, Question 112, which asks us to consider if we burn 1,000 grams of natural gas, how much energy do we get out? So natural gas is actually not a pure gas. It's made up of methane, about 88.4% by mass, and ethane, about 11.6% by mass. And here are their respective molecular weights. We've also been told that we have a heat of combustion for methane of negative 891 kilojoules per mole, meaning if we burn 1 mole of methane, 891 kilojoules of energy are released. However, we're not given the number for ethane. We'll have to calculate that ourselves. But to start off, let's just figure out how much of each gas we have by mass and convert that number to moles. So we have 88.4% out of 100% times 1,000 grams of natural gas. And that's going to give us 884 grams of methane. Now, if we take that number, 884 grams times 1 mole of methane over 16.04 grams, we can get the number of moles of methane, which is equal to 55.23 moles of methane. Similarly, we can do this for ethane. 11.6% out of 100% times 1,000 grams of natural gas times 1 mole of C2H6 out of 30.07 grams of ethane is going to give us 3.79 moles of C2H6. And so, with those numbers in mind, we can now move on to calculating the heat of combustion of ethane, which we don't know. And we'll take these on to another slide. So I've set up the reaction here for the combustion of ethane, where we have ethane gas, oxygen gas, going to CO2 gas and water liquid. So our process here is to take the sum of the heats of formation of the products, CO2 and water, and subtract the sum of the formation energies of the reactants, ethane and oxygen. We just need to know the stoichiometric coefficients to each of these terms. And so, let's write down the number of elements and atoms that we have on the left and on the right side of the equation. We have carbon, hydrogen, and oxygen on the left, 2 carbons. We have 6 hydrogens and 2 oxygens on the left. And on the right, we again have CH and O. And we have 1 carbon from CO2, 2 hydrogens, and 3 oxygens. And so, we now can set about balancing the equation. I like to start with the carbons. So I'll pick red, and I'll say, let's balance the carbons. We have 2 on the left, 1 on the right. Let's put a 2 in front of our CO2 and change our numbers around. So this becomes 2 carbons, and now instead of 3 oxygens, we have 5. And we still have 2 hydrogens. And so now our carbons appear to be balanced, 2 and 2. So now we can try to balance our hydrogens. 6 on the left, we have 2 on the right, and we can add 2 at a time. So let's put a 3 in front of our water molecule. 3 here brings us to still 2 carbons. Now we have a total of 6 hydrogens. And now we have 1, 2, 3, 4, and then 5, 6, 7. We have 7 oxygen atoms. Now we're looking good for balancing carbon and hydrogen, but oxygen doesn't look like it's going to balance. We can only have even numbers of oxygen on the left side of the equation. So to fix this, let's just multiply everything we've already done by 2. So with green, I'm going to put, instead of 1 ethane, let's put 2 ethanes. And let's change our other coefficients to 4 here, 4, and 6. And so if we write in the 6, we can rebalance one more time, and we'll determine what we need to put here for the oxygen coefficient. And so we have now 4 carbons on the left side, 12 hydrogens, and still 2 oxygens. And on the right side, we now again have 4 carbons. We still have 12 oxygens, but now we have a total of 14. So 4 times 2 is 8, plus 6, 14 oxygen atoms on the right side of the equation. And that's an even number. So now, in order to get the right number of oxygen atoms, we just need to put a coefficient of 7 here. And now we can look up the heats of formation of ethane, oxygen, CO2, and water, multiply them by their appropriate coefficients, and subtract them here, where the symbol sigma just means we add 4 times the heat of formation of CO2 and 6 times the heat of formation of liquid water. And we subtract 7 times the heat of formation of oxygen and 2 times the heat of formation of ethane. And the phases are very important. I just didn't say all of them. And so that gives us delta H of combustion is going to be equal to, and I've done this on paper, but we can look up the numbers and plug them in, negative 3,120.8 kilojoules per mole of ethane, C2H6. And so, if we now take the numbers of moles that we have our heat of combustion of methane, and now we have our heat of combustion of ethane, we can now start to actually figure out how much energy we're getting out of 1 kilogram of natural gas. And so to do that, let's draw a line away from our givens. We would have 55.23 moles of CH4 times negative 891 kilojoules per mole. Our moles will cancel, and we'll be left with the amount of energy we get from burning only the methane portion of our natural gas, negative 49209.93 kilojoules, a pretty large number. The same approach for ethane, 3.79 moles C2H6 times negative 3,120.8 kilojoules per mole. Again, moles cancel. And we get negative 11,827.8 kilojoules. And so all that's left now is to sum these two numbers. And so adding these together, we can get a final answer for the amount of energy we get for burning all of this natural gas, which is mostly methane and a little bit of ethane, negative 49209.93 plus negative 11827.8. And that gives us negative 61037.7 kilojoules. And to convert that for significant figures, we have negative 6.10 times 10 to the 1, 2, 3, 4 times 10 to the 4th kilojoules, which is equal to negative 6.10 times 10 to the 7th joules. So hopefully, this helps you understand how we can determine heats of combustion by looking at a chemical reaction and looking up heats of formation in tables, and also how we can use percentages and masses to figure out moles and then use heats of combustion to determine how much energy we get out of burning a certain substance. Thank you.